Let's see here. There we go. All right, I'll begin with a word of prayer. I think everybody who's here is here. That much seems likely. So, Heavenly Father, we thank you for this day. Again, I thank you for this class and this opportunity we have just to meet and study your creation. Help us to glorify you when we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's just look at the solution of the quiz here for just a minute. So I ran through some of this stuff like last class, but I just want to talk through it just a minute more because I think if I was to ask this question or something like it again on the test, you'd have a shot at it. But you're probably just not up to speed yet with some of the algebra here. But the algebra is really not too bad. Mostly because I told you the eigenvalues are 1, 7, and 8. So generally speaking, for 3 by 3, I usually at least give you guys one eigenvalue. That way you can factor the cubic, because generally speaking, when you look at the determinant of a minus lambda I, you get a third order polynomial. And so just to factor those in the wild is kind of a bit much. But if I tell you one of the roots, then all of a sudden you can factor out a quadratic, and then you can solve a quadratic, right? So there's a slightly stronger version of this problem that's possible if you have more time and you're a little bit more prepared, which is not where you guys were yet, which is why I graded this quiz extremely generously. So anyway, so eigenvalue 1, I solve a minus I times u equal to 0, which gives me these 3 equations here. And after some squinting and tilting my head, I can easily see that w is 2v, and then I just plug that up into this other equation, and I can make everything in terms of v. The u, v is v equal to v, and the w. So that's the name of the game, is you want to find one of the variables that you can write the other 3 in terms of. All right, that's what you're after here, right? You know that there's going to be infinitely many solutions because it's an eigenvector problem. All right, so that means that the solution set will have a parameter. You just need to figure out which one it is. Also, logically, there can't be 2 parameters in any of these because there's always at least one eigensolution for each eigenvalue. So if you have 3 distinct eigenvalues, you're going to get 3 lines as solutions, so to speak. All right, there can't be 2 parameters in the solution here. So the next one, 7, I looked at the equations and I was like, oh, okay, well, the last 2 equations are the same equation, obviously, right? So I can take either one of these and solve for u, v equals minus u, and then basically I just plug that back up in here, and that gives me w in terms of u, right? So I want everything in terms of one of the variables. I choose u in this case for eigenvalue 7, and I put a 4 there because if I get a fraction, I just choose the parameter so that the fraction goes away, just to make things who wants fractions, right? Did I tell you guys a story about my son? He wasn't allowed to play in the playground and have fun. You guys know what FunQuest is? So FunQuest has a rule that if you're over 10, you can't play in the kids' playground. But my 11-year-old really wanted to play with his brother, who's 7, in the playground. So he devised a scheme. When he got to the desk, he told them, they asked how old you are. He's like, I'm 10 and 7/6. 10 and 7/6. And they gave him the 10-year-old band. So you too can cheat ordinary folks if you learn about fractions. So anyway, yeah. So now fractions are Matthew's friend, is what he says. So anyway, so this one, eigenvalue 3, you get these. Basically, it's pretty obvious from this that u is free, which I anticipate that's going to make v and w both 0 when I look at the equations. And in fact, that's what happens. The middle equation gives me v equals to w. Then if I plug it into either this or that equation, I get the, oh wait a minute, this one gives me v equal to 0. Duh. And then if you put that with the middle equation, v equals to w, then we get v equals w equals 0. All right? So I just wanted to go back through this because I want to point out that if you had everything, like if you were thinking through everything correctly, you have plenty of time to solve these equations, actually. Even in the in-class quiz last time, yep.
How did you get v equals negative 2?
V equals what?
Negative u.
V equals negative, where are we talking about? Oh, so if I divide the middle equation by 2, that gives me minus v plus w. Oh, wait a minute, that's supposed to be a w. Yeah, that's just supposed to be w. Did I use that?
You did.
Oh, man. Rats. Oh. So I should have v equals to minus w. So let's see here. Well, fortunately I haven't posted it yet. At least I'm not showing it to you guys or anything. Let's see here. So yes, we will make mistakes. All right, so v, hopefully you don't make mistakes. So let's see here, v equals to minus w, right? And v equals minus w. For star star, replace star star with v equals minus w. Then my top equation, minus 2, rats, minus 2u minus v plus 4w. That tells me that v equals to 4w minus 2u. Which then gives me 4w plus 2w, I think. Because v is, oh no. Hold on a second. I'm too close to it. So I have v equals minus w. Oh, come on. Which variable am I going to keep here? Well, which one should I keep? I'm going to keep the w. So if I do that, I need to solve this for u. So this gives me u is 1/2 of 4w minus v, I believe, which would be 1/2. My w is w, so 4w, and the v was minus w, so that's plus w. So I think I get 5w over 2 if I haven't made a dumb mistake, which means that my vector, let's see here, we're doing, I can't read my own writing. Is that 2? Yeah, 2. So we've got u2. I was using w as the parameter. So I've got 5w over 2 here. My v was minus w, and my w is w. So I'm going to put w equals to 2. u2 equal to 5 minus 2, 2. Let's see here. Does that work? Or have I made another mistake this morning? Let's see here. 4 minus 4 minus 2, 8. 0. I mean, if I wanted to give a more robust check, I would multiply the matrix times this vector and see if I actually did get 7 times the vector, What I'm doing right now is not the best check, because if I made an error in setting up the matrix 7 minus a minus 7i, then I'd still be married to that error here in my check. But did it work? Did we get 0 here? So I get minus 20 plus 4 plus 16. Well, that's a good sign. And down here I get 4 minus 4, and then I get 8 minus 8, also known as 0. Whee! Wee-hoo! All right. So yeah. So sorry, I will try to fix this before I post it in the Canvas, but that was supposed to be like, so U2 we should use 5 minus 2, 2. All right. Now, none of you lost points because I wasn't grading off the answer, I was grading off effort and general proximity to the answer. So you either earned a 9 or a 10 on this quiz if you did it. If you got a 9, you're further away from the truth. If you got a 10, there were strong elements of truth on the quiz, at least in one of the problems. So anyway, so are we good now that I've fixed this? Thank you for pointing out the error. I do appreciate it. Super helpful. And that is an important thing in this course, right? If you make an error, you do need to like figure out how you're going to address it and fix it, right? So yeah, you're welcome for illustrating that. So long story short, this should have been 5 minus 2, 2 there. And so this is how we put together the general solution, right? We have e to the eigenvalue times eigenvector, and then e to the eigenvalue times the eigenvector, e to the eigenvalue times the eigenvector. This is a third order problem, which means the general solution must have three constants in it like this, all right? So we got that? Okay. So the second problem here, we have, the eigenvalue. Did you get the stuff on the board? Okay, cool. The eigenvalue ends up being 3 repeated. So then I go looking for my eigenvector. I only get 1, 1, 0. A lot of you got that. Yay. Excellent. And then what do you do with that? Well, you can use that to make a solution, right? But so this wasn't expected of you on the quiz, but I want to show you like the rest of the problem since we're here. It was to find a generalized eigenvector of order 2, right? So I solved the chain condition, which is the vector I don't know yet, equals to the eigenvector I already know. Solve that. I get v equals to 1, u is free. So I choose u equal to 0, which gives me the generalized eigenvector of 0, 1. And then I multiply that by the matrix exponential, use the magic formula for 3, and there it is. So, there gets to be a point after we've worked through the magic formula enough times that you know what's happening, right? So maybe you don't need to go through the magic formula every time. I'm just trying to emphasize what the logic is here. But if you want the takeaway message, the takeaway message is if you have a generalized eigenvector of order 2 and you've got that is resting above the eigenvector, u1, then you write down the solution e to the 3t times generalized eigenvector plus t times eigenvector. That's the solution. This happens every time in this kind of situation. And so there you go. And of course we also have the e to the 3t u1 solution that most of you wrote down. And so the general solution here has the form c1 e to the 3t times this plus c2 e to the 3t times that. All right. Okay, so any questions? I didn't require you to do the generalized eigenvector thing on the quiz, but that might appear on the test, for example. Yeah.
So with free variables, so are they like, so when free, like they can just equal anything, right?
Well,
you can make them whatever you want.
You can't make them 0 if it makes the vector 0. I could make u 0 here because the v was already 1. So like if you think about what it would have meant if I chose u equal to say 7 instead of 0 like I did in this solution. What that would have done is it would have added a 7 to, it would have put like rather than a 0 there would have been a 7 in the u2, like 7 7 1. And so if you think about what that would, if I put a 7 I would have had like a t plus 7, right? 1. So what that would have been doing is basically adding 7 more of these. It would have essentially been adding another copy of this solution into the second solution. So like there's always an ambiguity in terms of like how we set up solutions. You can always, if y1 and if r1 and r2 are solutions, then I can also like take a bunch of copies of r1 and add it to r2, and it'll still be the case that R1 and the modified R2 are solutions. We should talk about this more systematically, like what I'm talking about, because there's the so-called linearity of the problem allows for us to like take solutions we have and build new solutions. And sometimes that's helpful to understand like what the significance would be of making a different choice than we made, which in this case was 0. But if you chose 1, it wouldn't have been wrong. It would just been a different answer. Is that?
Kind of, because I'm just wondering why like, 3 variables you should like just 1. Like, is it just for simplicity? Like,
Yeah, just for simplicity of the answer. You could choose it to be pi or 42, whatever floats your boat. The one choice you can't make is 0 if it makes the vector 0, which is why I could make it 0 for u2 here, because v was 1. That's what freed me up to make the free choice as 0. So again, like the structure here is that you're looking at an equation where you're trying to solve AU equals to lambda u for u not equal to 0. Like that's what we're looking for. We're looking for an eigenvector solution. And as such, yeah, go away. The thing is, if you look at it, you always have a times the 0 vector, right? Which means that we're definitely in the situation that there's not just a unique solution to the equation, because there has to be the non-zero solution and at least one other solution, right? Which means that the system is consistent. It's a consistent system, but it's not a unique solution, right? So like what that then means, since we're working over either the real numbers or the complex numbers, is that there's not just one solution, there's infinitely many. There has to be a free parameter in the solution. But what we're doing is we're building a general solution, and we just want as many free parameters as we need. So like what we do, is we find R1, R2, Rn solutions to dr dt equals to ar, right? So we find these n solutions, and I don't want them to be families of solutions. I want them to be specific solutions, so that when I write down the general solution, this thing, I want these variables c1 through cn to really be the only variables in the solution, and selecting those variables will fix an initial condition, or we're given an initial condition and we have to fix the variables, right? Now, for that to be a general solution set, then as we talked about, for it to be a fundamental solution set, we do need linear independence of these n solutions, right? And so we talked about how we can put them in a matrix, and if the determinant of that matrix is non-zero, then they're a solution. It's a fundamental solution set. And we talked about how the matrix exponential, the columns of the matrix exponential provide such a solution set. But anyway, it is the nature of the game that we expect our eigenvector algebra problems to always have sort of more than we want, so we just have to pick one of them. Or you can have problems where you have like a repeated eigenvector, a repeated eigenvalue, like it could be repeated twice, and it might be that you get 2 free parameters in the solution, and then you can pick, then you have to somehow find 2 things from that. That's a little bit more complicated. Maybe we'll look at that in another example. But all right, so let's go back to some basics here, which is the linearity. So if we have dr1 dt equals to ar1, right? And we have dr2 dt is equal to ar2, then if you look at ddt of, say, c1r1 plus c2r2, what do you get? So we can pull the constants out, right? We can pull the constants out, and then what did we assume dr1 dt was? Well, it was ar1, right? And this was ar2, right? And so if you look at it, we've got a times CR1, C1R1 plus C2R2, right? What's that tell us? So, R equals to C1R1 plus C2R2 solves dr dt equals to AR. I'll get out of the way here. So what am I saying? Let me put it into words. What I'm saying is that a linear combination, all right, a linear combination of solutions to a system of differential equations in so-called normal form, right? But let me just say it this way. A linear combination of solutions to a linear differential equation is, guess what? A solution to the same differential equation. Now this, I'm assuming here that we're talking about a homogeneous differential equation, right? So like, I could rewrite this. Well, this is the homogeneous. This is the homogeneous case. We'll talk about the non-homogeneous case a little bit later this week. All right. So this is the homogeneous system. So that's what I was just talking about, like in my response to your question was like we can add solutions together and we still get a solution, right? You can add a multiple of one solution to another and you still get a solution, right? We good? All right, so let me do a symbolic example. Let's see, suppose we have non-zero vectors u1, u2, u3, u4, such that a minus, let's say 7i times u1 is equal to 0. And then a plus 11 times I u2 is equal to, well, let's say u4 is equal to u3, and a plus 11i u3 is equal to u2, and a times u2 is equal to minus 11 times u2. So given that A is 4 by 4 matrix, solve dr dt equals to AR. So I want to do at least one of these examples in class where we don't have a matrix with numbers, we just have like algebraic information about the matrix, and let's just work through how the solution looks like in this case, because that way we won't be distracted by any kind of silly arithmetic mistakes I happen to make about finding one of these vectors, right? This also makes for a nice test question for me because, you know, I can see whether or not you understand the general scheme of how we put the solution together without burdening you with the trouble of solving 4 equations and 4 unknowns 4 times, right? For example here. So, first of all, from this one, I can see, so like I'll tell you right off the bat, we have, you know, we can say x1 Oh, my bad. Well, I've been trying to use r lately. So r1 equals to e to the 7t u1, and let's call it r2 equals e to the minus 11t u2 as eigensolutions. I know that from this right here and this over here. Right? So because those two equations tell me that u1 and u2 are eigenvectors respectively with eigenvalue 7 and minus 11. Do you notice the difference in how the number appears? So like when I have a, see like this one here, if I was to rewrite it in the same way, this would give me a times u1 is equal to 7u1. And that reveals that the eigenvalue here is 7, right? Whereas this tells me that my second eigenvalue is minus 11. All right? How about the other conditions, though? What do those tell us? Yeah, how about this one? Like, what if I take a plus 11i squared times u3? What's that give me? It gives me a plus 11i times u2, which gives me what?
Right side is 0, right?
Right, yeah, because this is equivalent to a plus 11i times u2 equal to 0, right? So you got to be able to see your way back and forth between these two algebra equations. But you're right. So this is 0. Aha. So what's that make u3? That means u3 is a generalized eigenvector of order 2. See, because when you multiply it by a plus 11i on u3, you get u2, which is not 0, and yet the squared, a plus 11i squared on it gives you 0. Yeah? So I can figure this out then. I've got an R3, which I can do e to the ta times u3. And so just getting straight to the point here, we're going to use eigenvalue minus 11. So I do minus 11t times u3 plus tu2. All right? That is my generalized eigensolution. Right? Yep.
Could you restate what U3 was?
Sure. So generalized eigenvector of order 2 with lambda 2 equals to minus 11. Now, what about 4? Yeah. What about this guy right here? What can we do with this? So let's try that out down here. So I've got a plus 11i, and let's multiply it by a plus 11i again. So a plus 11i u4 equals to a plus 11i u3. What happens then? What's a plus 11i times u3? Well, we're given that that's equal to u2. All right. And then a plus 11i cubed times u4 is equal to a plus 11i times u2, which is, as we figured out in the far right of the board, 0, right? So what's this all mean? This means U4 is generalized eigenvector order 3, you know, with, again, eigenvalue minus 11. So, what does that tell us? So I skipped the details of the magic formula in the red right here, right? But I won't skip it this time for the third one, just so you can see what's going on again. So we have R4 equals to e to the ta times u4, which we can rewrite as e to the minus 11t times I plus t times a minus, well, plus 11i plus t squared over 2 a plus 11i squared plus dot 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 all times plus dot 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 all times u4. See? It's good that somebody put that there. Whoever did such a thing. So that gives me e to the minus 11t times u4, right? What's the matrix times u4? Well, the matrix times u4, well, that's given to be u3, right? So I get plus t times u3. And then I've got my t squared over 2. What's a plus 11i squared times u4? Well, that worked out to u2, right? So that puts a u2 here. And there you go, that's the end of it. So like if we have a generalized eigenvector of order 3, we get a t term and a t squared term. Right? Now let's put it all together. So thus R is equal to C1 e to the 7t u1 plus C2 e to the minus 11t u2 plus C3 e to the minus 11t times u3 plus tu1 oh, u2, right? u2 tu2, wasn't it? Yeah, u2. And then plus C4 e to the minus 11t times u4 plus t times u3 plus t squared over 2 times u2. There you go. And that is the general solution in this situation. So the way this is done is you find all the eigensolutions that you have. Great, you can just write those down because e to the eigenvalue times eigenvector is the eigensolution. And then we use the matrix exponential and the magic formula plus the chain conditions, which I gave you in the problem statement, to formulate the other solutions. And that's how it goes. And there's always enough of them, all right, because the matrix exponential is, in fact, an invertible matrix, which means that it has linearly independent columns like you'd like. All right. So that's as far as we can go in terms of systems where we have enough eigenvalues, all right? But sometimes we don't have enough eigenvalues, all right? So like, what do I mean by that? Well, there are problems which we cannot solve with the method that we have thus far. We need something else. Something is missing from our current technique, all right? So what is that? Remember I mentioned before, can I erase this? Not yet? No, okay. I guess I can write over. Well, you guys will remember all this, right? So the next thing up on our list of things to conquer is the problem of complex eigenvalues. And so here's the deal. If we have the determinant of a minus lambda I is equal to 0 for lambda equals to alpha plus I beta, where alpha and beta are real and beta is not equal to 0, then a vector u, which we usually use the notation a plus ib in here, is a complex eigenvector with eigenvalue lambda if a times u is equal to lambda u. And what condition do you think I need to state about u? Yeah, u is not equal to 0. Otherwise, this job would be much easier. We'd just be like, oh, 0 works. We're done. Always. But no, we need non-zero u. So a minus lambda I times u equals 0. So this should be totally unsurprising. I'm not writing anything different than we've done already, right? What's the difference? Well, that's not entirely true. What's different is that lambda now can be a complex number. The cool thing about this, guys, is if I calculate d dt of e to the lambda t times u, it is still true that that is lambda e to the lambda t times u, which is equal to e to the lambda t times lambda u, which is equal to e to the lambda t times au. If this is an eigenvector, complex eigenvector with eigenvalue 0, eigenvalue lambda for the matrix A, right? So what am I saying? Of course, you can bring the e to the lambda back inside, right? This is a e to the lambda tu. Now, oftentimes I'll use a z here because people oftentimes use z for complex variables. And this is a complex solution, so I could call z vector, right? And over here, here's z vector, and what are we seeing? We're seeing that we still solve the equation dz dt equals to az, right? It's a complex solution to dr dt equals to ar. Now, you might wonder, well, how is this any different than what we've already done? Well, the devil's in the details, right? Because here, e to the lambda t and u are both complex valued. So I probably need to, get into details here for you to understand that, and we will. But let me just kind of tell you this much at this stage in the game, which is that we can write z vector as a sum, a complex linear sum of a real and imaginary solution. So like, we can write z vector is equal to, let's say, x vector plus y vector, where x and y are real solutions. So how do you calculate a derivative like this? You just do it component-wise. So like dz dt is dx dt plus I times dy dt. That's how that works, right? And so that's going to be equal to a times z, right? But what's that equal to? That's a times x plus iy vector, right? So what do we got here? Okay, you can multiply this out, right? So here we have ax plus I times ay. So I don't know how much you guys know about complex at this point, but you can't avoid it, right? It's in science, it's in engineering, it's certainly in math. And so let's talk about it. When we have a complex vector equation, we get two real vector equations, you see? So I have, here's my real part. See that? The real part's dx dt. What's the real part over here? It's just ax. Now, we're assuming, what are we assuming about the matrix A? we're assuming A is a real matrix, all right? So all of the complex, the imaginary part is made explicit with that I. I is the square root of minus 1, right? So the real part has to be equal to the real part. And the imaginary part has to be equal to the imaginary part. See, so like this piece right here must match that piece right here. So what does that mean about, what do we have? We have dx dt equals to ax, and we also have dy dt equals to ay. So, by the way, sometimes people use the notation x is the real part of z, and y is the imaginary part of z. Notice that the I is not included in that. It's, right, rides along. So what I'm trying to tell you all is that if we had a complex solution, right, then the real and the imaginary part are separately solutions to the underlying real differential equation, right? Now this process of taking a real differential equation and replacing it with a corresponding complex differential equation, I call complexifying the problem. But most people just say let it be a complex solution, and they don't tell you that you're doing something sophisticated there, but they really are. But we do it, so everybody else is doing it, right? Makes it okay. Now I've already kind of given it away. How are we going to find these complex solutions? Well, with complex eigenvectors. That's how. All right. So let me just give you a definition here. E to the alpha plus I beta times t is equal to e to the alpha t times cosine beta t plus I times the sine of beta t. So this is how we deal with so-called complex exponentials. An exponential with a complex multiplier, it gives you a real exponential and a complex linear combination of sine and cosine, where the arguments of sine and cosine are based on the coefficient of I, the beta here. So let's see here. So for example 2, if I had, for instance, z vector equals to e to the, let's say, 2 plus 3i times t times, let's say the vector 1 plus I, 2 minus I, all right? I'd just like to show you what the real and imaginary parts are of this complex vector. This is the kind of thing I was talking about, right? This has the format e to the lambda t times, u. That's the format here. In this case, my u is 1, 2 plus I times 1 minus 1 in my made-up example here. So this would be what I usually call A, and this is what I usually call B. I think that's the nomenclature, the notation which is used in section 9.6 of the text if you prefer to read that. All right? Okay, great. Then what? So this is e to the 2t times cosine 3t plus I times the sine of 3t. And then I've got, 1, 2 plus I times 1 minus 1. And so how do we find the real and the imaginary parts of that? We just multiply out, okay? Just multiply it out. So I get I'll leave the e to the 2t out front, but that's going to give me a cosine 3t rather, times 1, 2, minus the sine of 3t, 1 minus 1. And then we've got plus I times e to the 2t, sine 3t, times 1, 2, plus cosine 3t, I'll get out of the way here in a second, times 1 minus 1. So this first business there is the real part of my complex vector solution. And the second part, without the I, is the imaginary part of my complex vector solution. So what this shows you, by way of example, is that if we have a complex eigenvector solution to a differential equation, we get not just one real solution, but two separate real solutions. And we can prove, in fact, that these are distinct, linearly independent solutions. So we really are getting, honest to goodness, two solutions from each complex eigenvector. It's a twofer. This is good news, because it halves our work in some sense. But the bad news is we have to do complex arithmetic, right? But it's not too bad. Any questions? So this may be your first exposure to the imaginary exponential. It depends on like what other math you've taken and stuff. But generically speaking, this e to the I beta t equals to cosine beta t plus I sine beta t. This is known as Euler's formula, or Euler's identity. And it can be understood in any number of ways. Like you could derive this from looking at the Maclaurin expansion of the exponential and looking at how like i's to a power either give you plus or minus 1 or plus or minus I. And if you do that and regroup the terms in the Maclaurin expansion for the exponential, you'll get sine and cosine just like we have here. But this identity has been known since like the mid-18th century, and it's still important today. It's especially important for understanding this material. So next time what we'll do is we'll actually look at a 2x2 system where we get a complex eigenvalue, and we'll find the complex eigenvector, and then we'll use this technique of ripping the real and imaginary parts of the solution off to construct the general solution. So that's almost all there is to this story. The only other missing part is that you can also have generalized complex eigenvectors, and then again you have to take the real and imaginary parts of those solutions. But I think that's enough for one day. So thanks, guys.